From the earliest moments of human consciousness, we have gazed at the heavens, charting the cycles of the sun and moon. This celestial dance, so vital to our lives, marked the beginning of our understanding of time. Ancient civilizations, from the Egyptians to the Mayans, developed intricate calendars, monuments, and timekeeping devices. They observed the rhythmic patterns of the cosmos, weaving them into the fabric of their cultures and beliefs. These early astronomers and mathematicians laid the foundation for our ongoing quest to unravel the secrets of time. Time, in these early observations, was inseparable from the celestial bodies that governed our days and seasons. The rising and setting of the sun, the waxing and waning of the moon, these predictable events formed the bedrock of our early calendars. Yet, even as we measured its passage, time itself remained an enigma, a fundamental force shaping our lives, yet evading easy definition. What was time exactly beyond these celestial cycles? This question, pondered by philosophers and scientists for millennia, lies at the heart of our fascination with this elusive concept. The nature of time has been a subject of debate and speculation for centuries. Ancient Greek philosophers like Heraclitus likened time to a river, constantly flowing and ever-changing. This idea resonated through the ages, shaping our understanding of time as linear and unidirectional. We experience time's passage as a one-way journey, from the past through the present and into the future. Yet with the birth of modern physics, our understanding of time underwent a profound transformation. In the early 20th century, Albert Einstein shattered our Newtonian conception of time as absolute and unchanging. His theory of relativity proposed that time is not a universal constant, but rather a relative concept woven into the very fabric of space-time. This revolutionary idea opened up startling new possibilities, challenging our intuitive understanding of time's passage and suggesting that perhaps the river of time could flow at different rates, even in reverse under certain conditions. From a scientific perspective, time is often defined as a measure of change. It is the progression of events from the past to the present and into the future. We observe this progression in the physical world around us, from the decay of radioactive isotopes to the expansion of the universe itself. This unidirectional flow of time, often referred to as time's arrow, is a fundamental aspect of our reality. Yet, the fundamental laws of physics, with the exception of thermodynamics, are time symmetrical. This means that the equations governing the behavior of matter and energy work equally well, whether time moves forward or backward. The arrow of time, from this perspective, seems to emerge not from the fundamental laws of physics, but rather from the initial conditions of the universe. Why time flows in one direction, from a state of lower entropy to higher entropy, remains one of the most profound unanswered questions in physics. Albert Einstein's theories of special and general relativity revolutionized our understanding of time. He demonstrated that time is not absolute, but is relative to the observer's frame of reference. Time, according to Einstein, is intertwined with space, forming a four-dimensional fabric known as space-time. The flow of time in this context is not constant, but can be influenced by factors such as gravity and velocity. One of the most startling predictions of Einstein's relativity is time dilation. Time dilation suggests that time slows down for objects moving at high speeds or experiencing strong gravitational fields. This effect, while seemingly counterintuitive, has been experimentally verified using atomic clocks flown on high-speed jets and satellites. These experiments have shown that time truly is relative, a concept that challenges our everyday experience but is essential for understanding the nature of the universe on a grand scale. To fully grasp Einstein's revolutionary ideas, we must abandon our Newtonian intuition of time as a separate entity. Instead, imagine a four-dimensional fabric where space and time are interwoven. This is space-time, the very essence of our reality. Within this framework, we can visualize time not as a river flowing at a constant rate, but as a dimension, much like the three spatial dimensions we experience daily. Just as we can move forward, backward, left, or right in space, Einstein's theories suggest the possibility of movement through time. Of course, our everyday experience seems to contradict this. We cannot simply hop into a time machine and visit the dinosaurs. However, the mathematics of Einstein's equations leave the door open to such possibilities, at least in the realm of theoretical physics. When we look at the universe on its grandest scales, the concept of time becomes even more intricate and awe-inspiring. Astrophysicists study distant galaxies and quasars, using these celestial objects as cosmic clocks to peer back into the universe's history. The light from these distant objects, traveling at the speed of light, takes billions of years to reach us, providing a snapshot of the universe as it was eons ago. These observations paint a picture of a universe not only expanding in space but also evolving in time. Time, in this context, is not merely a measure of change but an integral part of the universe's very existence. As the universe expands, time marches forward, and our understanding of its nature continues to evolve alongside our expanding cosmic horizons. The idea of time travel has captivated the human imagination for centuries, fueling countless science fiction stories and sparking endless debate among physicists. While the practicalities of building a time machine remain firmly in the realm of science fiction, Einstein's theories of relativity do not explicitly rule out the possibility of time travel. In fact, they offer tantalizing hints about how such a feat might be achievable, at least in theory. One proposed method for traveling through time involves traveling at speeds approaching the speed of light. According to Einstein's theory of special relativity, time slows down for objects approaching the speed of light relative to a stationary observer. If a spaceship could reach such incredible speeds, time for the travelers inside would pass much slower than time for those left behind on Earth. This phenomenon, known as time dilation, suggests that time travel into the future might be possible, albeit technologically challenging. Another intriguing possibility for time travel arises from Einstein's theory of general relativity, which describes gravity as a curvature in space-time. According to this theory, massive objects warp the fabric of space-time, much like a bowling ball placed on a trampoline. This warping of space-time is what we experience as gravity. However, general relativity also allows for the possibility of wormholes, theoretical tunnels that connect two distant points in space-time. If wormholes exist, and if they could be manipulated, they might provide a shortcut through space-time, allowing travelers to journey vast distances instantaneously or even travel through time. However, the existence of wormholes remains purely theoretical, and even if they do exist, the technological challenges of harnessing them for time travel would be immense. The concept of time travel is rife with paradoxes, thought experiments that challenge our understanding of causality and the nature of time itself. One of the most famous is the grandfather paradox, which asks what would happen if a time traveler were to go back in time and kill their own grandfather before their parent was born. Would the time traveler cease to exist? If so, how could they have traveled back in time in the first place? These paradoxes highlight the complexities of time travel and the limits of our current understanding. Some physicists believe that time travel paradoxes might be resolved by the existence of parallel universes or by some yet unknown mechanism that prevents such paradoxes from arising. Others suggest that time travel might be possible, but only within certain constraints, such as the inability to change past events that have already occurred. Time, from our earliest attempts to track its passage to our most advanced scientific theories, remains one of the universe's most profound and enduring enigmas. We have made incredible strides in understanding its nature, from the cycles of the cosmos to the curvature of space-time. Yet fundamental questions remain. Why does time flow in one direction? Is time travel truly possible? And what role does time play in the grand scheme of the cosmos? These questions continue to captivate physicists, philosophers, and dreamers alike, pushing the boundaries of our knowledge and inspiring us to explore the universe and its mysteries with ever-increasing wonder and curiosity. As we delve deeper into the nature of time, we may unlock not only the secrets of the universe, but also a deeper understanding of ourselves and our place within the grand tapestry of existence.